Hi, Assalamualaikum and greetings to my respected panels. My name is Muhammad Haidir bin Hamdan. I am from Department of Mechanical Engineering Technology, University Tun Hussein On, Malaysia. And my bachelor degree project supervisor is Dr. NOFRIZALIDRIS bin DARLIS. And now I'm going to present my bachelor degree project's poster with the title of Hydrodynamics Analysis on Liquid Bulk Transportation with Different Driving Cycle. Firstly, we go to the abstract. Liquid bulk transport is one of the most important modes of fluid package transport, whether by sea or land. Thus, flexi tank is one of the alternative ways for transporting the fluid package. However, there are cases reported by industry regarding on the leakage of the flexi tank during transportation. The purpose of this study is to determine the suitable filling volume capacity on flexi tank by using computational fluid dynamics (CFD). Hydrodynamics performance such as wall shear stress, volume fraction, sloshing forces and dynamic pressure will be analysed on different filling volume capacity and different driving cycle, which is 5%, 10%, 15% more or less from the reference capacity, about 24,000 litre, and different driving cycle which are city suburban and freeway driving cycle. The results indicates that varying the filling volume capacity of the tank affected the liquid sloshing behavior and hydrodynamics performance of the tank. The worst wall shear stress occurs at the filling volume capacity of minus 15%, as it is increasing the shear stress by 80% at city suburban and 35% at freeway compared to its reference value. Following that, both speed profiles have its best dynamic pressure at the filling volume capacity of plus 10%, as it is reducing the dynamic pressure by 60% at city suburban and 47% at freeway from its reference value. Thus, it is recommended that the filling volume of plus 10% is suitable for the flexi tank. Hence, this study benefits liquid bulk transportation by increasing filling volume capacity and optimizing hydrodynamics performance. Hence, for the introduction, flexi tank in the market claim that its maximum capacity is 24,000 litres. However, there are still cases reported by industry regarding the leakage incidents. The rising concerns in shipping liquid is the sloshing effect. So this project aims to analyze the effect of hydrodynamics performance due to different driving cycle and determine the suitable filling volume capacity of the flexi tank using the numerical analysis of flow performed using CFD software, SolidWorks flow simulation. Next, we move to the literature review. Firstly, by A. Altonen, 2015, in his study on how are flexible tanks becoming a solution for wine-in-bulk transportations, states that flexi tank is a one-way transportation method as the flexi bank is not reusable, making the contamination risk of the products low. So these findings shows that why industry players are prefer to use flexi tank as their methods of transporting the fluid package. Next, by Goodrich, stated there are some cases to be reported that the package of flexi tanks found to be damaged and leakage upon arriving at the port. These findings shows that there are possibilities of the flexi tanks to leak during transportations is exist. Next, by N. Clark et al. In 1999, state driving cycle is intended to depict a driving pattern in a particular environment, such as an urban or highway, to limit vehicle exhaust gas emissions and fuel consumptions. Therefore, in this study, driving cycles of city suburban and freeway was used to analyze the hydrodynamics performance. Lastly, by Roshan Ambade et al. 2014, by its study on CFD analysis of sloshing within tank. It analyzed the volume fractions and pressure variation on elliptical tank and subjected to sudden impact. From these findings, it shows that previous research mostly used CFD to analyze hydrodynamics performance. Therefore, in this study, CFD will be used to analyze the hydrodynamics performance on the flexi tanks. Next, we continue with the methodology. From the previous study, there are variations of software being used, such as NC's SPH graphic simulations. And for this study, the simulations used to analyze the hydrodynamics performance is the SolidWorks flow simulations. And for the velocity and capacity, there are also differences between all the researchers, as it is comply with their objective. And for the type of flow, it can be seen most of the researchers use transient state to study hydrodynamics performance. Hence, this study also use transient state. Next, for the geometrical modeling. In this study, the geometrical modeling was developed using the CAD software SolidWorks 2019. And next, for the meshings, in these studies, the fluid domain, the meshing was being done at the fluid domain and the internal walls of the flexi tank. And next is the boundary conditions. As can be seen, it is for the speed profile, it is based on 2 driving cycles, which is city suburban and freeway. And then for the reference, it can be seen from the table the variety of list for the filling volume capacity. And for the mesh validation, in this study, it was carried out from the first level of refinement until the best level. And in this study, the best level refinement achieved is at the 3rd level. Next, after the mesh quality validation was achieved, the flow simulation was proceeded, and then the results was analyzed, and lastly, the documentation. Next, we move to the results and discussions. For the volume fractions, it shows that the liquid moving at the opposite direction of the flexi tank movement direction. During sloshing, the liquid hits the back, front, and the top of the flexi tank walls. This shows that there are possibility of the leakage to happen. And if we look at the t equal to 0 seconds, 100 seconds, and 300 seconds, the liquid sloshing behavior for both driving cycles is nearly same. But at t equal to 379 seconds, it has a slightly difference. For the city suburban, the liquid is in a steady state as it is fully stopped based on the driving cycle conditions. And for freeway, it is not in steady state and still sloshing as it is not fully stopped. Parameters like wall shear stress may contribute to the leakage of the flexi tank. Next, we move to the wall shear stress. The figure shows the wall shear stress at the top of the flexi tank for both driving cycle. From the contour, it can be seen that decreasing the fill level led to increasing the shear stress. This is because the sloshing behavior is more violent with a lower filling volume than the higher filling volume. The red region indicates the maximum shear stress. As can be seen from the figure, for the city suburban, the minimum fill level minus 15% has the reddest region with the value of 0.177 Pascal and 80% worse than the reference. While the maximums, which is plus 15%, has no red region with the value of wall shear stress 0.0301 Pascals and 70% better than the reference value. While for the freeway, the figure also shows that the highest stress occurred at the fill level of minus 15%, where the value of its wall shear stress is 0.1585 Pascals, which is 35% worse than the reference filling volume shear stress, which is 0.1177 Pascals. It shows that the shear stress increases when the filling volume decreases due to the rigidity of the liquid in the flexi tank. For the dynamic pressure, the graph shows the dynamic pressure variations of different filling volume capacities over time. The filling volume capacity of minus 10% has the highest dynamic pressure among other filling volume capacities from the graph. The average dynamic pressure for the filling volume capacity of minus 10% along the 379 seconds is 2,830 Pascals for city suburban and 2,554 Pascals for freeway. The reference capacity of 24,000 liters has the average dynamic pressure value for 840 Pascals for city suburban and 1,175 Pascals for the freeway. As the reference capacity has leakage issues, the filling volume capacities of minus 10% can be considered as rejected, as with those values of pressure is raising the risk for the leakage incident. The graph shows the filling volume capacity of plus 10% has the lowest dynamic pressure for both driving cycle conditions. City suburban average dynamic pressure is 333 Pascals, while for the freeway dynamic pressure is 625 Pascals. These values are 60% and 47% respectively better than the reference values. Hence, this analysis shows that filling volume capacity of plus 10% is the best as it is sloshing with the lowest dynamic pressure. Next, moving to the sloshing forces. The graph shows the sloshing forces over the time. The graph's trend shows that the sloshing forces increases when the filling volume decreases. From both graphs, it is occurred due to the sloshing behavior differences. When the filling volume increases, the flexi tank liquids becomes more rigid. Hence, it sloshes less violently compared to the sloshing behavior with lower filling volume of the liquid. From the graph of city suburban, plotted slosh force is higher at the range of 266 seconds to 379 seconds, which is 32,162 newtons. Then the plotted at the range 0 seconds to 150 seconds, which is 11,686 newton. This is occurred due to the deceleration time experienced by the flexi tanks being shorter than the acceleration time. However, for the graph freeway, the slosh force is higher during the acceleration at the range of 0 seconds to 276 seconds, which is 106,526 newton. Then the slosh force during the deceleration, which is 1900 to 19,284 newton, that can be observed at the plotted graph. However, for the graph of the freeway, the slosh force is higher during acceleration at the range of 0 seconds to 276 seconds, which is 106,526 newton. Then the slosh force during deceleration, which is 19,284 newton, that can be observed at the plotted graph, range at 344.6 seconds until 379 seconds. This is affected by the motion experienced by the flexi tank, which is the city suburban and freeway driving cycle. Based on the driving cycle, motion at the city suburban from 0 seconds to 379 seconds needed the flexi tank to experience motion from 0 meter per seconds to 13 meter per seconds in 81.1 seconds and 13 meter per seconds to 0 meter per seconds in 58 seconds. Besides, for the motion at the freeway driving cycles, the flexi tank experienced acceleration from 0 meter per seconds to 21 meter per seconds in 196.5 seconds duration time. Then it decelerates from 21 meter per seconds to 14 meter per seconds in 34.4 seconds duration time. Hence, the filling volume capacity of plus 50% is the best because it has the lowest slosh force, with percentage difference of 27% for city suburban and 40% for freeway, better than the different slosh force. Lastly, for the suitable filling volume, after considering the hydrodynamics performance analysis in this study, the suitable filling volume can be determined. The determination being made as shown in the table. After taking into account the percentage difference of all parameters for each filling volume capacity, it can be considered that the suitable filling volume for flexi tank is plus 10%, as its percentage differences indicates that it is better than the reference values of all the parameters. And as the conclusions, the effect of hydrodynamics performance due to different driving cycles was analyzed. The determination of suitable filling volume capacity on 20 feet container size was accomplished in this study, which is plus 10%, equivalent to 24,240 liters. It was ascertained that the hydrodynamics performance of fluid changes as the filling volume capacity increases. I think that's all from me. Thank you for your time and Assalamualaikum.